Hello everybody, my name is Hakam Al-Omari from Miami University. Today I'm going to talk about the srcClone paper by Matthew, Stephen and I. Motivation. As system grow, maintenance can become more complicated and costly. Clone detections can help in maintaining systems. Type 4 semantic clone identification is challenging as it can be difficult to determine semantically similar components. Program slicing is a widely used and well-known approach for comprehending and detecting semantic properties of the software. As a motivating example, consider the code snippet in Figure 1a. When compared with code snippet in Figure 1b, the code is similar semantically. Both perform the same overall computation, but Figure 1b replaces control statement with a different one. Both are implemented by different syntactic variants. Now, the current textual-based one, most of the functional-based techniques are unable to take the semantically similar clone scenario as the one proposed in 1b. Research overview. We take code clones based on the similarity of the slicing information between code fragments. The hypothesis here, the semantic clone is equal to the slice similarity. To do that, we start by converting the source code into the source.ml format. More about source.ml in the next slides. We use source slice to build a three-tier system dictionary with a slicing profile for all slicing variables. We encode the slicing profile into slicing vectors by means of its embedded slicing information. The slicing information we use is the def, use, dependent variables, pointers, and call function for each slicing variable. This is how the slicing profile is look like. Number 4, we use efficient hashing and near-neighbor algorithm to cluster these vectors with respect to the distance between them. So this is the pipeline at the top. If you see, we have the source. We convert this to source ML or XML representation. We use our source slice tool to generate the slicing profiles. Then we generate the slicing vectors. Then we use the LSH hashing to cluster and detect the clones. More about the srcML tool. It's available online on the website mentioned on the title. srcML format is an XML representation of the source code. This format provides direct access to abstract syntactic information to support the static analysis. This syntactic information is used to identify program dependencies as needed when computing the slice. For more details, please refer to the paper. In this work, to extract the slicing information, we used our lightweight source slice tool. It's available on this website on the title. Source slice implements a forward decomposition inter-procedural static slicing technique. It's lightweight, highly scalable, and not BDG. Before start talking about the detection process, here's an example how we use the srcML and source slice. We convert the source code into the srcML format. This is the srcML format. And then we use this format as an input to the source slice to use a slicing profile that have the following format. If you take a look on this format, we can see for each variable there is one profile, and in each profile there is a def, use, dependent variables, pointers, call functions. More about this in the next slides. To show you how we create the slice profile, we take the same example from the previous slides. You can use equation number 1 here to create a slice profile at the variable granularity level, which is equal to the union of all forward slices on all statements that define or redefine that variable. Or you can use equation number 2 to create the slice profile at the method granularity level, which is equal to the union of all forward slices for all slicing variables inside that method. Table 1 shows the slice profiles derived using equation number 1. Table 2 shows the slice profiles derived using equation number 2. If you take a look for table number 1, we can see that the I variable, for example, is defined in statement number 4 twice, is used in statements 4, 5, 6. There is 2 dependent variables on I, broad and sum, and the pointers and call function sets are empty. We can use equation number 3 to create a slice profile at the file granularity level, but this is not the case in this example because each file contains exactly one function. Some definitions we use in our paper. We consider two code fragments semantically similar if their slices are similar. The code fragments in our work represent a slice profile, either on the variable level or method level or the file level. Two slice profiles are similar if if their slicing vectors are sigma similar. Two slicing vectors are sigma similar if the similarity between them is less than a threshold. And we will talk about the threshold later. These are the clone type definitions in our context. We use exactly the same standard definition agreed upon in the literature. Please refer to this slide or in the paper to read more about this. But we are interested with type 4, the semantically similar code segments. In this slide, we try to show you how we create the slicing vector. For the same example, table 1 represents the variable level, and table 2 represent the slicing profiles calculated at the method granularity level. Here is the slicing vectors. Basically, it contains the def, use, dependent variables, pointers, and call functions. In the method level, we add one dimension represent the number of variables, and in the file, we add the number of methods inside the file. Table 3 represents the slicing vectors for the variable level and function level. If you take an example here, the I variable, for example, we have 2, 3, 2, 0, 0. 2, if you take a look for the table number 1, you can see that I is defined twice in the statement number 4. It used 3 times in statement number 4, 5, and 6. We have 2 dependent variables, prod and sum, and pointers is empty, call function is empty. Let's take an example of the function level. For example, sum prod. We have 6, 4, 2, 0, 1, 4. If you take a look at table number 2, you can see that the sum prod is defined from 1 to 6 times. And this is the union of all the variables inside the function. The use is from 4 to 7, 4 times. We have 2 dependent variables. Pointers set is empty. And the call functions, we have 1 function. And we have 4, the last vector or dimension is 4. This is the number of variables inside the sum prod. And this is the same for the sum prod E. Similarity and matching, we handle near missing clones by comparing vectors looking for similarity rather than exact equality. So instead of matching the entire slicing vector, we compare instead dimensions for similarity. We use the equality sensitive hashing to minimize the number of comparisons. If you look at the last 2 lines in this definition, if the distance between the 2 vectors is less than R1, then the probability that those 2 vectors hash to the same bucket is greater than P1. If the distance between the 2 vectors is greater than R2, then the probability that those 2 vectors hash to the same bucket is less than P2. We use Hamming distance to measure the distance between 2 vectors, which is equal to the number of bits or positions that different. We use the Hamming distance because the lower bounds, the P1 and P2, are known, which is equal to 1 minus R1 over D and 1 minus R2 over D. And this is a proof in this lemma 3.1. Here is the approximate near neighbor. We use it to generate the CRANN set of V, the approximate near neighbor set that contains all the candidate pairs of the clones. And this is the algorithm to showing that. There is no need for normalization and transformation as others in our work because we generate a slice profile for each variable. And here we have a quick example. Please return to the paper to read specifically about this example. We successfully detect type 1 and type 2 clones. And here's a quick example. Now if you compare this code to the top right corner. Now then the text string based techniques, okay, the 3 segments are different because I have different value and the variable is change the name in the segment 3. In text line based techniques like NCAD, for example, the first two are similar, not the third one. But in our work like CC Finder and CloneDR, we have all three are clones because they are in our work they have the same slicing vector. And also we are successful to detect type 3 and type 4 detection clones. Now if we take a look for those two codes in program A and program B, you can see both are the same, except like we have additional two variables, start and finish, at line 12 and line 13, and two statements using those variables in line 17 and 18. That's the only difference between B and A. In our work, so we generate the file level slicer profiles. Here the file level slicer profiles, and we can see that all vectors are similar at the variable level except for the start and finish. And since start and finish does not exist in the first code snippet, which is program A, so we delete those, so we end up with the same slicing vectors, and we end up that those two codes are similar. Two research questions we try to address in our evaluation. Does source clone identify accurate clones? Is source clone scalable and efficient? Because the number of dimensions in our vectors are fixed, we can specify the probability for the locality sensitive hashing. In our case, it's equal to 1 minus R1 over 5. 5 is the number of dimensions. Now, if we work over the variable level, P1 will be equal 80, but in the method level, we have 6 dimensions, so it will be equal 83. And the file level, the number of dimensions in the slicing vector is equal to 7, so we will end up with 86. We compare our tool to commanders and gables. Those are BDG and using slicing. These are the system in table 6 that we use in the comparison. And as we can see, the Linux kernel version is equal to 6.6 million lines of code. And these are the results on table 7. And as you can see, Commander took 1 hour and a half almost to find 800 clone groups. In our tool, within less than 2 minutes, we find more clone groups, like more than 1,000. In the Linux kernel, Gable took like 9 hours to find 255,000 clone group, and we find more clone group within just 3 minutes. In order to verify the precision of our tool, manually we checked some of the returned results against Commander. So Commander was successful to return the highlighted code, like 2 copies of this code snippets, like in figure A and figure C. But in our tool, we returned 5 copies of this. And if you take a look for the table F, you can see that the slicing vector at the FP3 variable, all of them are the same. Here we use the famous 16 scenarios proposed by Roy to evaluate our tool. We were successfully identified all the scenarios with some minor loss in the precision, especially in scenario number 3 and 4. So 1 and 2 are successful, 3 some loss because some line deleted or added, and in 4 because I is defined twice in S4D. In this table, as you can see in the last row, this is our tool comparing to the other tools used by Roy's, okay? And all of those scenarios, the coverage for our tool is 100, and the precision is very high. Conclusion and future work, we presented our initial result for detecting code clones using program slices. We believe this is a new perspective on semantic clone detection, and we employ a scalable, lightweight slicing tool to compute the necessary slicing data. We encode slicing profile as vector and hash them efficiently using the LSH at 3 levels of granularity. We implemented our algorithm in a tool called srcClone. Our evaluation demonstrated that it is practical and scaled to million lines of code. In the future, we plan to compare srcClone with slicing based and non-BDG based state-of-the-art tools. And we will use some modern data sets like Big-Clone Bench. I'm happy to answer your question on Slack or shoot me an email. Thank you.